Okay, so what we're going to do here is convert from expressions to strings in the process we call pretty printing. Let's do a visualization of what goes on, how we're going to do this. We've got two different ways that we might do it. We're taking our example expression, 2 plus 3 times 4. What we're going to do is show how you can think of pretty printing that, first of all in a bottom-up way and then in a top-down way. And the top-down way will show us how we're going to write our recursion. So let's think about a bottom-up pretty print. What would it do? Well, it would first of all convert the numbers at the leaves into strings. So we'd have 2 and 3 and 4 as strings. And then we combine those. For the multiplication, we combine those into the string, open parenthesis, 3 times 4, close parenthesis. And then at the top level, we can combine those strings into the string that represents the whole expression. So you can see the values flowing up the tree in that way. But we can also think of it in the reverse way. So we can think of doing it top down. We can think what we're trying to do is pretty print an expression that is an addition. So what will it look like? Well, it'll look like open parenthesis, something, plus something, close parenthesis. And if somebody were to give us the string representing the left expression and the string representing the right expression, we'd have the whole answer. We can think of that. We can get the string for the left expression, we can get the string for the right, and once we've got those, if somebody gives those to us, we're able to write the thing at the top. And that gives us a guide about how we write the recursion. We can think of, if only somebody were to give us a present of the values for the left, values for the right, it would be easy to write for the value for the whole thing. And that's what a recursive definition looks like. You define the result for the complex expression in terms of the results for its subcomponents. But I'm running ahead of myself a bit here. Let's backtrack a bit and think about what the definition should look like. First of all, what we can do is write a spec which says what type the function that we're going to write is. And what this spec says is that there's a function print that takes as an argument an expression and it returns as a result a string. So there we've said what our intention is. That's the type of what we want to do. Now remember, the type expr has 4 different cases, one for a number, one for a variable, one for an add, one for a multiply. We can build a definition that reflects precisely that template. So we have one case for each of those 4 possibilities. We have a print of a number, print of a variable, print of an addition, print of a multiplication. And what we'll do now is fill in those in turn. So first of all, how do we print a number? And the number is n. What we have to do is turn that number into a string, and the way we do that is the built-in function called integer to list. Slightly confusing, but remember that strings in Erlang are really just lists of numbers, the numbers being the ASCII values of the characters. So integer to list is the thing that turns that number into something that is a string representing the number. In a similar way, when we have a variable whose name is an atom, what we have to do to print it out is turn that atom A here into a string. And what we do is use atom to list, and that does that conversion. So we've dealt with the 2 cases of the things that we can have at the leaves of the tree. Now, what about an addition? The addition is going to have 2 subcomponents, E1 and E2, which are themselves expressions. So what we do is build the representation of the whole expression from the values for those sub-expressions. So the addition looks like open parenthesis, print the left sub-expression, then the addition symbol, then the right sub-expression, then a close parenthesis. All joined together using the plus plus operator, which is Erlang's way of joining together lists, or in this case, strings. So that prints the addition for us. You can guess what the multiplication will look like. It's exactly the same, except that we put a multiplication symbol between the 2 sub-expressions. And so there we've completed our definition, which mirrors the type definition precisely. We have a case for each of the possibilities, And in the case that the type definition is recursive, the cases of addition and multiplication, the function itself is recursive. So we have that almost mechanical way of going from the type definition to the functions that work over that type. So that's nice. And this is one of the nice things about functional programming. We see types being reflected in definitions. Another very nice thing about functional programming in Erlang and other languages is that we can then very simply work with these sorts of definitions. So we've got this definition and we can think of these rules as, these function clauses here, as rules for writing from left to right. And so we can do the pretty print by hand, step by step, using these clauses of the definition as rules. So let's try that out. It's the same example again. So let's print out that structure which represents 2 plus 3 times 4. So what have we got at the top level? We've got a print of an add expression. So the rule that matches is the one I've shown in purple here. And what we do is turn what we have to evaluate into what we see on the right, making the appropriate identifications, the appropriate substitutions of E1 and E2. And what that gives us is this expression now, which has 2 calls to print inside it. The first one is a call to print for a number. The second is a call to print for a multiplication. So let's see how that works out. First of all, let's think about printing the number. What I've done is highlight the thing that we're wanting to print. And what we can do is rewrite that into the corresponding right-hand side, which is the integer to list. And I think I'll take the liberty of actually doing the integer to list here when I do the rewrite. And we've got a second expression here. We've got the print of a multiplication. And you can see that now highlighted. And what I'll do there is also rewrite that. And that rewrites to 2 further calls. So let's do both of those at once. You can see one of the nice things again about functional programming is when you do evaluation, at least when there are no side effects, you can do these things in parallel. So we can rewrite that to say, the first call has become the string with just 2 in, and the second call has nested as 2 more calls to print, but these are both calls to print num, which will, in due course, turn into strings for the number 3 and the number 4. So that will turn out to look like this. So what we have now is a long string joined together with plus plus, which when we join all the pieces together, we have precisely what we would expect. So perhaps no surprises here, but what you're seeing is the fact that you can use these rules in a completely transparent and mechanical way to go from the expression we wanted to evaluate to its result. And that really is very nice. So the model underlying the functional programming part of Erlang is this very simple model of expression evaluation. So when somebody asks, what's the model that underlies Erlang, you can say that's it. If you ask somebody, I sometimes ask my students, what's the model that underlies Java, they scratch their heads and go rather quiet, because the model there is much more complicated. It's about classes and inheritance and blah, 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 with some mutable state underneath. Whereas here, what you do is expression evaluation, turning a left-hand side into a right-hand side. That's in the purely functional core, of course. When you're doing message passing, things get a little more complicated, but not that much more so. So simple model of evaluation is a firm foundation for what we build on top of that. So what we've done here is that we've seen how to use the type definition to give us a template for a recursion. We've written the recursive definition of printing, and we've seen how we can use those rules to work out step by step the result of that functional definition. And that's a pattern we're going to follow in the next lecture, where we take a look at expression evaluation.